Hi everyone. This video is designed to help you with assignment number 9 in your resource pack, and it's going to deal with acids, bases, and their chemical and physical properties. So in your reference tables, you have table K and table L that list for you an example of common acids and common bases. And when we think about what acids and bases are, they're really just special types of solutions that have compounds dissolved in them that have very particular chemical properties. And whenever we talk about acids and bases, we inevitably have to talk about this scale, the pH scale, because it's how we define what is acidic and what is basic. And if you happen to find a solution that has a pH of 3, you would find that you're on this end of the scale and that you're in acidic territory. Anything with a pH between 1 and just below 7, which is our neutral, is an acid. And anything with a pH above 7 is going to be categorized as a base. The issue immediately presented is, how am I going to know what the pH of a particular solution is? You can't tell just by looking at it. Unless, of course, you've put an indicator into your particular solution and you've been given a clue about what its pH might be. And that's what Table M is all about. These are a list of common indicators that you could find in a chemistry laboratory. And the way you read Table M is like this. We see that methyl orange is an indicator that can either be red or yellow. And it changes from red to yellow over a certain range of pHs. So methyl orange can be used at any pH, but between these two ranges, it's starting to change between its red and yellow colors. So let's say we're at the very far left-hand side of our pH scale, pH 1. It has not yet changed color, so methyl orange would be red. And in fact, it would be red up until it hit pH of 3.1. Then it starts to change gradually from red to yellow. So this is kind of ambiguous territory for methyl orange. It's going to be kind of an orangey type color. But as soon as it hits 4.4, methyl orange decidedly turns yellow. And anything above pH 4.4 will be yellow according to methyl orange. So if you dropped a couple drops of methyl orange into a solution that had a pH of 13, we're well above 4.4, so it has definitively changed into its yellow color. You can use the same concept to read the rest of these indicators. If, for example, phenolphthalein is put into a solution with a pH of 2, you'd very clearly be able to differentiate it from a solution with a pH of 10, because the one with a pH of 2 would be colorless, and the one with a pH of 10 would be bright, bright pink. So we can get an idea of about where we fall using those indicators from Table M. And what those tell us is just how acidic or just how basic we might be. If you used, let's say, just a pH strip and found that the pH of vinegar is about 3, whereas the pH of hydrochloric acid is about 1, and you wanted to know why you can put vinegar on chips and be happy, but you can't put hydrochloric acid on chips and be happy, is the relationship between how acidic you are and what your pH is. If I move from pH 3 down to pH 1, each jump represents something becoming 10 times more acidic. So what we really have is 10 times 10, a solution that is 100 times more acidic than vinegar. If you move in the opposite direction, of course, you're going to get something that is 10 times 10 or 100 times less acidic. You can do this jumping anywhere along the pH scale to figure out exactly how much more or less acidic something is. What that actually means, though, is all about the chemistry. If you're more acidic, you have more ions that make you associated with an acid. And if you look at your table K, you're going to see that hydrogen is in every single acid that's listed. That's because if you dissolve acids in water, they produce the H plus ion. This is sometimes written as H3O+, which if you look on table E is just another way of writing hydronium. H3O+ is just H2O plus H+, so you can treat these two things interchangeably. If you're becoming more acidic, then what that means is you're getting more H plus ions dissolved in water, or more hydronium ions dissolved in water. Bases then, we're decreasing the amount of H+, and what we see replacing the H+, is the OH- ion, or hydroxide, as is listed on table E. A lot of the bases on table L do contain this OH- ion, and as you'll see, they're always bonded to a metal if they have OH in them. So no covalent thing is going to be basic, even if it has that OH at the end of it, because it always has to be OH- and some positively charged metal. The only issue with this definition is that NH3 is on table L, and NH3 certainly does not contain OH-. We've had to toy around with what our definition of what an acid is and what a base is because of this fact. So this traditional definition is oftentimes called the Arrhenius definition of acids and bases, that acids make H+ and bases make OH-. This serves our purposes for 90% of all scenarios. However, we had to come up with this alternate definition to take into account that some things that are basic just don't produce OH-. So the language that we're going to use to describe that is that acids are H+ donors. And what we mean by that is that they donate H+ to water. So that matches what Arrhenius already told us in the first place. More H+ equals more acidic. The alternate theory kind of does the opposite for bases. If more H+ equals more acidic, that should mean that less H+ equals less acidic or more basic. So instead of calling bases OH- producers, we're going to call them H+ acceptors. And what that means is that bases take H+ out of the water. And if you're removing H+, you're scrolling over to the right on this pH scale and becoming more and more basic. So if you put H+ in, you're an acid. If you take H+ out or accept H+, you're a base. And hopefully this helps sort of piece together some stuff on assignment number 9 for your resource pack. But keep in mind that it's going to be important to understand the pH scale, definitions of acids and bases, and how to use table M to figure out what color indicators mean about where you fall on the pH scale itself.